This is Generalized Linear Models with examples in R, Chapter 3, question 3.29. Okay, so we're going to look at a data set called fluoro, and it has two variables, dose and time, so radiation dose and time. Okay, and so, and in the paper, I guess, that produced this data, it says that one might postulate the radiation dose received is related to the total procedure time. Okay. So we're going to do some things with all of this, and yeah, so we'll start with one. So first, you need to install and load the GLM's data package. You need to get hold of the data, which is fluoro, and here I'm just calling it D, as is my normal convention. So we can see what the first few rows look like. Okay, so we have time, we have dose. Okay, good enough. And so now we are supposed to plot exposure dose against exposure time. Okay, so and then comment. So when we do this, I think there's a couple of things. One is there seems to be maybe kind of a curvilinear relationship going on, probably, maybe. And there's also some heteroskedasticity here. So before going on, I just want to play with a few transformations here. Well, first of all, this curvilinear relationship kind of makes sense, right? Because the minimal dose cannot be negative, right? So we're bounded at 0. So as we start to stack up to 0, get close to 0, we can't have data points below there, right? But as we move forward in time, right? Well, now the dose can go, arbitrarily high, and so I think that kind of helps to explain this curvilinear relationship a little bit, some of it, and also some of the heteroskedasticity. Because again, when you're very, very low on, when your dose is very, very low, there's not a lot of values. There's not going to be a lot of spread around 0. Okay, so partly because you can't go below 0. Okay. Anyway, I think there's some more stories you could tell about why the heteroskedasticity takes place. Maybe, well, whatever this procedure is, it could be that that the dose of the radiation is not consistent through the whole time, or whatever. But whatever. Okay. So anyway, getting back on track here, I want to also plot dose against log time, and then log dose against log time, just to kind of see how those relationships start to change. And so when we plot a dose against log time, it's hard to say that that's really better or not. Okay. But now when we go log, it certainly seems to have taken care of a lot of the curvilinear problems and the heteroskedasticity problems. What I didn't try here, maybe I'll just try it just for fun here, is log dose against time. Let's just see what this one looks like all by itself. That's interesting. Yeah. So so I'm going to continue with this log plot here, just because that's what I've done. But we might have also explored just log dose. But anyway. All right. So now we need to fit a linear regression model of dose on time. Okay, then plot the residuals and show that the variance is not constant. Okay. Now I'm actually going to do each of these models that we looked at here. Okay. Let me get all of those up. Okay. So I have just dose on time, dose on log time, and log dose on log time. Again, we could have also done log dose on time, but that's okay. So we're going to make these models, and then we're going to look at the residual plots here. So here we go. You know what? I'm going to clean this up. I'm just going to pull these residual versus fitted plots here. So give me a second. Okay, now we have just residual versus fitted plots here, and I did that by, just specifying that I want the first plot. Okay, so so this is for the normal model. Okay, the dose over time. Okay, and then this one right here is for the log dose log time. All right. Now, so we're supposed to, by the instructions, we're supposed to eyeball this and show that the variance is not constant. Or at least that's how I read that. And, I guess I would agree that it seems that there's some heteroskedasticity taking place here. But it would be nice if we could quantify this. I don't think we've done this in any of the other videos, but it occurred to me while I was doing this one, maybe based on how that was worded, that we can actually do a test for this. I don't know how big of a fan I am of this test, but it is interesting. We could manipulate it until we were, were comfortable with the output. Okay, but this test is called the white test. Okay, and it's very basic. If you want to learn more about it, I'm just going to give a cursory view, but you should go to this video by Ben Lambert, and if you have not watched Ben Lambert's stuff, you really should. It's fantastic. It's about 10 years old now, but it's all incredibly well done. So, but anyway, so the idea behind this, what's called the white test, okay, is that we are going to regress the residuals on the fitted values, right? So here we have the raw data, or I shouldn't say the raw data, but we have the data points representing residuals for particular fitted values, okay? And we've drawn kind of this, curvy line of best fit here, some kind of lowest line or whatever. But we can actually try to find we can actually run a regression here and then look to see if the result tells us that that there's heteroskedasticity here, okay? And so the way that we do that is, sorry for the code being a little bit of a mess here, but we're going to run a normal linear model, and our output is going to be the residuals squared. I'll talk about why residuals squared here in a second. And then we regress it against the fitted values. Now you'll notice that I'm using a polynomial, and I'll explain that as well here just verbally. But with all of this, we get an F statistic, and then we can look at the p-value for that F statistic, which is what I've done here. Well, we'll look at that here in a second. Okay, so why do we do the residuals squared? Well, it's because we're trying to test the assumption about the variance. And the variance, so our surrogate for variance is not the residuals, right? Because residuals can be positive and negative. The variance is always positive because it's the sum of the squared differences and da-da-da-da-da. And so our surrogate measure for that is going to be the residuals squared. Okay, so there's that. And now why are we? So now we regress it on the fitted values. Okay, so that's good. And now, but why are we using some kind of polynomial function here? Now you don't have to, but the reason is because our assumption says that for any one of for any value of our predictor variables, or any combination of our predictor variables, here there's just one, but we could have many, that variance is basically a random draw. It is in no way related to the predictor values. Okay, well, how do we get all of the predictor values into a regression? Well, we could just regress the residuals on predictor value 1, predictor value 2. But then we might also want their interaction, so predictor value 1 times predictor value 2, and so on and so forth. But if there truly is no relationship between the residuals and the predictor variables, then there shouldn't be any relationship between the square of the predictor variables or the cubes of the predictor variables, and so on and so forth, right? So rather than putting in all the predictor variables, we just simply put in the y values, the outcome values, and then by taking the polynomial, a polynomial of the fitted values, it is as though we are regressing on every x squared, every interaction, and so on and so forth. Okay. So, like I said, you should watch this video by Lambert. It does a better job explaining, but so I'm just kind of directing there. But anyway, so for each of these, we can get a p-value for the null hypothesis. The null hypothesis in this case being that there is no heteroskedasticity. Okay, so we do all that, and here's our p-values for the three models. Now, it depends on what your threshold value is, but these are all reasonably high, okay, far from what are typical p-values at which we reject the null hypothesis, okay? And so, in a way, the assumption of this question is, you could say it's incorrect, because the p-value is pretty high, so there's maybe not compelling evidence that there is heteroskedasticity here. Now, you might start to see a little bit of a problem with the white test, or really using these null hypothesis tests to test assumptions about the model, because in the model we probably want to okay, so if we're testing an interesting hypothesis, and so now we're testing the null hypothesis technically, but as evidence towards an interesting hypothesis, we want to be skeptical of the interesting hypothesis being true, right? So we make it hard to not just simply adopt the null hypothesis. But here, in doing that, we are basically kind of tipping the odds in favor of we don't find heteroskedasticity. In other words, our model's fine, don't worry about it. And that seems like the wrong attitude to have, right? It seems like we might want to be more skeptical of our model, and therefore, adjust the p-values accordingly. But anyway, this is how it's normally ran. I don't know if I agree with it, but nevertheless, what we can say is that using the log at least has the highest p-value, meaning that there is the least evidence for heteroskedasticity there. So I'm just going to move forward using that particular model. Okay. Part 3 is use various transformations of the response variable and do what we just did. But we've already done that, right? That's what the log and the log-log models were. So we've already done that. Okay, now finally, for parts 4 and 5, we're supposed to test the hypothesis implied by the quote in the original question, which is, here it is, one might postulate that radiation dose received is related to total procedure time. Interpret the final model. Oh, I'm sorry. So that's the quote. And then part 5 is interpret the final model. Okay. So I'm going to use, like I said, the log-log model. And as far as interpreting the model, so let me first reinterpret the hypothesis. Okay. The reinterpret of the hypothesis with the log-log model is that log radiation dose is related to total procedure log time. Okay. Or maybe log total procedure time. Okay. But anyway, so that's maybe not really important here, that distinction, because the hypothesis is worded a little bit loosely. But anyway, so we're going to test this by just running the summary on our model, and we go to the coefficient for log time, okay, and we see probably pretty compelling evidence that that log time, that log dose is increasing by about 2.8, log dose units for every, 1 log unit of time, or log time unit. Okay. So anyway, we will call that good.